So today what we're doing is we're still going to be talking about bond polarity and whatnot, but we're going to look at the bigger picture. We're going to start looking at molecules instead of just individual bonds. First of all, what we do with these individual atoms is we make what are called Lewis dot diagrams. It's pretty simple, really. All we have to do is look at the group number that they're in, which tells us the number of valence electrons, right? And we put that many dots around the symbol. So, for example, hydrogen is in group 1, so we put 1 dot with it. Beryllium, we'll just go ahead and go across. Beryllium is in group 2. We would put 2 dots by it. Those 2 electrons go into the s subshell, right? The s orbital together, and so we pair them up when we make the dots. Boron is in group 3. And for purposes that we might run into later, we don't pair these up. Carbon is in group 4, so we would have 4 valence electrons. Nitrogen's in group 5, so it has 5. 2 of them are paired up in the s sublevel. The other 3 are by themselves. Each p shell orbital gets an electron before they start to pair up, right? Yes? The question was, how do you know where to put the dots? Basically, it doesn't matter which side you put them on, but basically you pretend like there's a box around the element symbol, and you can put 2 dots on each side. Because the magic number is 8, right? The most we're going to have on any of these is 8. Oxygen would be in group 6. So it would have 6 valence electrons. So, for example, with oxygen, I could make them like this, or I could put pairs on the top and one side and leave single on the bottom and the other side. Doesn't really matter which way I do it. And then fluorine's in group 7. So it would look something like that. So this is just called Lewis dot diagrams. And what these can do is help you figure out how the molecules are made, how the electrons get shared in order to make the molecules. For example, a real easy one would be an HF molecule. Hydrogen's in group 1. Technically, this is going to end up being an ionic compound. Hydrogen's in group 1, fluorine's in group 7. So hydrogen becomes a +1 ion, fluorine a -1. But what we would show is fluorine's 7 valence electrons, and I'll use a different color for hydrogen to show it. Hydrogen's 1 valence electron, and if these were being shared instead, we would just kind of move hydrogen right in there. They would share those 2. This makes fluorine feel like it has 8, which is what it wants, and this makes hydrogen feel like it has 2, which is all it wants. Hydrogen's the exception to the octet rule, right? Everybody wants 8 electrons around it except for hydrogen. It only needs 2. Okay, so you can use electron or Lewis dot diagrams to help you figure out how the molecules get made, as far as, fitting together pieces. But there's a little bit more reliable method. Takes a little bit longer, maybe. It involves math, but in most cases, it's more reliable for figuring out how the bonds get made to make the molecule. Okay? And it's called, I call it the S equals N minus A method. Okay? S stands for shared, because that's what these atoms are doing, is they're sharing electrons so that each one feels like they have a full valence shell. N stands for needed, and A stands for available. And it can be, this method is a lot more reliable, like I said, for some of the more difficult molecules. For example, if I told you to write the, figure out the molecule, the molecular structure for carbon dioxide, you might have a hard time taking one carbon with 4 dots around it and 2 oxygens that have 6 dots around them and figuring out how they all piece together to make a molecule of CO2. But with this method, it actually becomes pretty easy. Okay? So first, what you do is you identify a central atom. Central meaning the one that's in the middle. All right? I'm going to get rid of these guys here. There's a few ways we can figure out which one's going to be the central atom. The most, well, the easiest way is which atom is there only one of. In this case, there's only one carbon. So it would go in the middle, and the oxygens would go around it. That's step 2. You place the terminal atoms. No, they're not ill. They're called, terminal means ending, right? So these would be on the outsides, the end points of the molecule. So place terminal atoms symmetrically. Am I missing a letter? Are the 2 ends in symmetrically? Think so? This doesn't look right, I'll tell you that much. Yeah, we'll go with it. Huh? It doesn't look like right either, does it? We'll just go back with 1M. I ain't no English teacher, so. Is it 2? Yeah, we'll go with 2. It's a weird word. We'll just leave it at that. So place the terminal atom symmetrically around the central atom. Another way you can identify a central atom is, typically it's the one with the lowest electronegativity. Carbon has a lower electronegativity than oxygen. Hydrogen can never, ever be a central atom because hydrogen can only make 1 bond. Oxygen usually isn't the central atom either. I mentioned hydrogen can only make 1 bond. Let's backtrack a little bit and look at these dot diagrams again. Again, hydrogen only wants to have 2 electrons, so it can only make 1 bond. As far as the rest of them goes, the atoms in group 2, they're going to make ionic compounds all the time. They're not going to make covalent bonds. They're not going to share electrons. Atoms in group 3 sometimes will make covalent bonds. Since they have 3 valence electrons, they can make 3 bonds. So group 3 can make 3 bonds. Group 4 atoms have 4 valence electrons. They can make 4 bonds. Group 5 atoms have 5 valence electrons, but 2 of them are already paired up. So you look at the atoms or the electrons that are all by themselves. There are 3 atoms. I keep saying atoms. There are 3 electrons that are all by themselves. So group 5 atoms, once again, can make 3 bonds. Group 6 has 6 valence electrons, but 4 of them are already paired up. So there are only 2 that are by themselves. So group 6 atoms can only make 2 bonds. And group 7 has 7 valence electrons, but 6 of them are already paired up. Only has 1 electron that's all by itself. So group 7 atoms can only make 1 bond. Okay. So we identify the central atom. We place the terminal atoms around them symmetrically. And then we do the S equals N minus A thing. So shared, the number of electrons that are going to be shared is equal to the number of electrons that are needed minus the number of electrons that are available. For the needed, again, all atoms, all elements need 8 electrons, except hydrogen. Which only needs 2 electrons. For the available, all you got to do is look at the group numbers, the valence electrons, and add them up. This pen is going to cause me problems. All right, so in this example, I've got 1 carbon and 2 oxygens. That's 3 total atoms. Are any of them hydrogen? No. So, since I have 3 atoms and none of them are hydrogen, I need 24 electrons. 3 times 8. I'll write that down over here. For the available, I've got a carbon that's got 4 valence electrons. And I've got 2 oxygens that each have 6 valence electrons. 2 times 6 would be 12, plus 4 more would be 16. So I've got 16 available. So if we need 24, we have 16 available. 24 minus 16 would be 8. These 3 atoms have to share a total of 8 electrons between them. Step 4, we figure out the bonds. Each bond contains 2 electrons. So all we do to figure out the number of bonds is take the number of shared electrons and divide by 2. So in this case, we've got 8 divided by 2. So we have 4 bonds. Typically, oxygen can make up to 2 bonds. Technically, we could make 3 if we do some funky stuff with it, but we'll just forget about that for now. So if each oxygen can make 2 bonds and the carbon can make up to 4 bonds, We need to put 4 bonds in here, but we only have 2 places to put them. So we put 2 on each side of the carbon, 2 bonds between the carbon and each oxygen. And there's our 4 bonds. So we place the bonds in there, basically symmetrically, paying attention to what elements can make how many bonds. Then we need to figure out the unshared pairs. To figure out the unshared pairs of electrons that are going to be left over, we take the number that were available, subtract the number that got shared, that would leave you with the ones that are unshared, and since they come in pairs, we divide that by 2. So we had 16 available. We shared 8 of them. 16 minus 8 would be 8, and then to pair them up, we divide that by 2. There's going to be 4 unshared pairs. We take those unshared pairs and we place them around the terminal atoms until they have 8 electrons. So our oxygens are our terminal atoms. Right now, each oxygen has 2 pairs of electrons in those 2 bonds. Okay? Each bond is 2 electrons. So since the oxygens each have 2 bonds, that's a total of 4 electrons. They want to have 8. So we can put an unshared pair here and an unshared pair here. That's 2 of our 4 unshared pairs. And that fills that oxygen up. It now has the 4 electrons from the 2 unshared pairs, plus 4 more that are in those 2 bonds. Do the same thing with the other oxygen and the other 2 unshared pairs. Now that oxygen has 2 unshared pairs, which is 4 electrons, plus the 2 bonds, which is 4 more electrons. So this oxygen now feels like it has 8 electrons. This oxygen now feels like it has 8 electrons. And the carbon in the middle, because it has 4 total bonds around it, and each bond has 2 electrons in it, feels like it has 8 electrons. And all of them satisfy the octet rule. All right. We'll take a look at one more example. Any questions about this so far? Okay. We'll take a look at another example. And well, let's see. Let's just do good old ammonia. NH3. Okay, so figure out our central atom. Well, there's only one nitrogen, and hydrogen can never be a central atom. So nitrogen's going to go in the middle, and we'll put the 3 hydrogens around it symmetrically. So now we can go to our S equals N minus A thing. As far as needed goes, We have one nitrogen that's going to need 8 electrons. But remember, the hydrogens, they only need 2. So if you see a hydrogen in your molecule, then as far as the needed goes, you have to put however many hydrogens you have in that molecule times 2 instead of 8. All right, 3 times 2 would be 6, plus we have the one nitrogen that needs 8, so we need a total of 14 electrons. Put on pen. How many do we have available? Well, that nitrogen's in group 5, so it has 5 valence electrons. And each hydrogen's in group 1, so they each have 1 valence electron. 5 plus 3 would be 8 total electrons. So how many are going to get shared? We take 14 minus 8, and they're going to share 6 electrons. Which means, how many bonds do we have? The answer is 3, so I wrote that down. 6 divided by 2, take the number of shared divided by 2, because each bond has a pair of electrons in it. And we've got 3 bonds. Well, that's convenient, because we have 3 places to put bonds. And each hydrogen can only make 1 bond anyway. So we should have known right away we're going to have 3 bonds. Unshared pairs, also sometimes referred to as lone pairs. If I ever say lone pairs, you know what I'm talking about. Again, for that, we take A minus S and divide by 2. We had 8 available. We only shared 6 of them. 8 minus 6 is 2. Divided by 2, we got 1 pair to put on here. Let's see. I said to put them around the terminal atoms until they have 8 electrons. Well, in this case, our terminal atoms are hydrogens, and they only need 2 electrons, and they already have them because of the bonds. So we cannot put unshared pairs on a hydrogen atom. Please, for the love of everything holy, be the class that doesn't put any lone pairs on a hydrogen atom. Okay? Or I might just snap. So, the rule is, I didn't say it before, but I'm going to say it now. The rule is, if the terminal atoms are already filled with the number of electrons they need, then any lone pairs that are left over go on the central atom, which in this case is good because right now this nitrogen just has the 3 bonds, which is a total of 6 electrons. It wants to have 8. So that lone pair is going to fill it up. Okay, so now each of these hydrogens feels like it has 2 electrons, which is all they want, and that nitrogen in the middle feels like it has 8. Anything that's not hydrogen is, in the end, going to feel like it has 8 electrons around it. Yes? All right. I feel like that's enough for today. We'll talk in more detail tomorrow about how to figure out what shape these guys have. And from there, we'll be able to figure out whether the molecule itself is going to be polar or not.